Hello and welcome to this video. In this video, I want to deal with case 3. That's the third case where we have complex or imaginary roots. So where we have complex or imaginary roots. I'll deal with this by means of an example because that's usually what's easiest to work with. Now, we already dealt with one example already. We already dealt with one example where we simply had an exponentially decaying sinusoidal function. So I'll deal with something that is a little more complex in this particular case. So we want to find the, let's say we're told to find the inverse Laplace transform of, well, let's just use 1 divided by, say, s plus 1 multiplied by, let's make this s squared plus s plus 4. Okay, let's say we have the system, and while crafting this example just now, I was just trying to make sure that this will actually give us complex roots, and I'm quite confident it will. So if we wanted to expand this, first of all, let's ask the question, this second order expression over here, can we decompose it into first order expressions? If we can decompose it into first order expressions, then this expression here, so okay, let me go ahead and write something down here. We have s plus 1, s squared plus s plus 4. The question is this: is there a way we can decompose this into k1 over s plus 1 plus k2 over s plus something plus k3 over s plus something? Now, if we can decompose this into real roots that are not repeated, then we can express it in this form. On the other hand, if the roots are repeated, then we will have s plus something here and maybe s plus something that way. Okay, if the roots are repeated, this is what we will have. But now, in this particular case, the question is, are the roots repeated or not? So let me take off everything else that we had here, and let's ask the question, are the roots here repeated or are they real? In fact, are they real in the first place? First question is, are they real? Next question is, are they distinct? Let's use our test. B squared, is it less than 4ac? So b is equal to, b squared is equal to 1 squared, which is simply equal to 1. 4ac is equal to 4 multiplied by 1 multiplied by 4, which is equal to 16. So 4ac is that now. So b squared is less than 4ac. Okay, b squared is less than 4ac. So we see that these are complex roots. How do we deal with this? By the roots being complex, that means that if we attempt to decompose this, what you will have will be something like s plus, say, a plus jb, and then that's as one denominator, and then another denominator will be s plus a minus jb. Okay, where a minus jb and a plus jb are the complex, or are the negatives of the complex roots. And now, since we do not like to work with complex numbers like this, and really we cannot say that in honesty, this gives us, okay, so let's go ahead and write this k2 and k3. Now, if we expressed it in this form, then our solution to this system will be the inverse Laplace transform of this system. So let me just say the inverse Laplace transform of this system would have simply been k1 multiplied by e to the power of minus t plus k2 multiplied by e to the power of minus a plus jbt plus k3 e to the power of minus into a minus jbt. Okay, this is our solution, and this, yeah, it might look weird, but it actually is our solution, and arguably there's nothing wrong with it. Now, okay, so these are complex numbers. How do you deal with these complex numbers? Let me rewrite this a little bit. You have k1 e to the power of minus t plus k2, and because this is a summation over here, we can as well write this as e to the power of minus a multiplied by e to the power of minus jbt. Okay, all I've done is expand this parenthesis over here, and I've explored the fact that if you multiply two items, the exponents add, up. So this is what we have over here. Now I'm going to add this to plus k3 e to the power of, I'll do the same thing over here, minus, oh, I left out the t over here. My apologies for that. E to the power of minus at multiplied by e to the power of, now this negative multiplied by negative, so that gives you positive, so you have jbt. So this is an expression that we now have. How do we go further? E to the power minus at is common to both sides, but you have a k2 and you have a k3. So you need to determine what your k2 and your k3 are. Then you can now look at this expression, e to the power minus jbt, e to the power of j, and then e to the power of jbt. And maybe we can use the fact that I believe your, do I remember this well now? Your cosine of, I think cosine at can be expressed as the e to the power of, if I remember well, jat plus e to the power of minus jat, and the sine of at is the same thing as being equal to e to the power of jat minus e to the power of minus jat. Please just check this this expression. I want to make sure that I didn't mix up this signs up. So you could actually use this expression to come up with, to discover this apparently as sinusoidal functions. But first of all, we have to compute our k2 and our k3. And to find our k2 and our k3, we're going to be using complex values. We're going to be working with complex numbers all along. Now, this is a lot of work, okay? And honestly, I don't think we want to bother going through all this trouble. So instead, let's do what we actually typically do instead. Okay, so let's do what we actually typically do. So let me come back here, and instead we have 1 over s plus 1 into just rewriting the expression we had earlier on, this expression we have earlier on, s squared plus s plus 4. Okay, now we want to decompose this into partial fractions. We will not decompose it like we did above over here. Rather, we'll decompose it as k1 over s plus 1, and we keep this term together. Okay, we keep this term together, plus, so our denominator will be s squared plus s plus 4. However, your numerator will now not just be k, rather will be two terms, k2s plus k3. Because this is a second order function in your denominator, we have a first order function in our numerator. So now with this expression, we can go ahead to decompose this into partial fractions. Okay, so we can now decompose into partial fractions. So if you want, whichever method you choose to use, let's go ahead and expand and combine this together. You have k1. So I'll combine this together and just equate that to the numerator over here. I hope this combining these two steps into one doesn't come out confusing to you. So I have k1 multiplied by s squared plus k1s plus 4k1 plus k2s plus k3 into s plus 1. Okay, so 1 is equal to all of this. Let me expand this parenthesis here. You have this being equal to k1s squared plus k1s plus 4k1 plus this will be k2s squared plus k3s plus k2s plus k3. Okay, so collect like terms if you want. This is k1 plus k2s squared plus k1 plus k2 plus k3s plus 4k1 plus k3. Is there any term left out? Okay, and all of this is equal to 1. So 1 is equal to all of this. Now, like we have done earlier on, we know that our k1 plus k2 is equal to 0 because there's no s squared term on this left-hand side. And we also know that our k1 plus k2 plus k3 is equal to 0 also, because there's no s term on this side. Now this just kind of works out beautifully for us. K1 plus k2 is 0. K1 plus k2 plus k3 is equal to 0. This implies that your k3 is equal to 0. This first term implies that your k1 is equal to negative of k2. Now your third term is what you have here. Your 4k1 plus k3 is equal to 1. We already know that our k3 is 0, so this implies that your k1 is simply equal to 1 divided by 4. Okay, k1 is 1 over 4. That implies that my k2 is equal to minus 1 over 4. Okay, so this is fine, and now we can plug this into our partial fraction expansion, and we're good. So we have that our function 1 over s plus 1 into s squared plus s plus, is it 4? Is equal to 1 over 4 over s plus 1 plus, I need to go back and check to make sure I'm not doing anything wrong. Yeah, s squared plus s plus 4, that's correct. K over s plus 1, then k2s plus k3 over that. Okay, so let's come back here. We have k2s, so that's minus 1 over 4s plus k3. K3 is 0. Let me just write that there. Plus 0 over s squared plus s plus 4. The first part is easy to deal with. Let's concentrate on the second part for now. So this is equal to 1 over 4 over s plus 1 plus, here we have negative 1 over 4s over s squared plus s plus 4. Now, to find the inverse Laplace, so the inverse Laplace transform of the first one is clear. The inverse Laplace transform of this second one is maybe not as straightforward. So let's go ahead and compute and find out what it looks like. The Laplace transform, now there's an s in the numerator, s squared in the denominator. This looks like a cosine function. So I would suggest that whenever you have a cosine function, just assume you have a constant, you have an exponential, and then you have the cosine function cos omega t. Okay, even if your constant is 1 and your a turns out to be 0, that is perfectly fine, but always assume this. Now if we found the Laplace transform of this, what we'll have would be k multiplied by s plus k multiplied by s plus a all over s plus a all squared plus omega squared. Okay, I believe this is the Laplace transform of this. Okay, so this is the Laplace transform of this. Maybe I'll pause this video at this point and I'll just pick it up from this exact point in the next video so that the video doesn't get too long.